Okay, so we're going to talk a little bit more about geometric optics here. And to give you sort of the background on that, we're going to start with talking about what light is. Optics is really where we look at how light acts in different materials. And it's not just visible light, it's all wavelengths of light. But we are most used to talking about the optics of, say, the eye or optical instruments or whatever. So largely in this section, we'll be talking about visible light, but there are different forms of light and they all behave in a similar fashion. So we have this concept that's going to lead us into the rest of the semester where light acts both like a wave and a particle. And this was not really understood until the late 1800s, early 1900s. But when we talk about light, we assume it propagates like a wave, meaning that all the stuff we've talked about with waves and sound and how electric fields and magnetic fields work, those are all applicable, but it gets absorbed and emitted more like a particle by an atom. So we're going to see both of those things when we talk about light. Now, all bodies emit based on their temperature, and part of what you're going to see in the lab is that effect. It's called a black body. Now, an idealized black body will emit only based on its temperature. It will absorb all wavelengths, but it will emit just on its temperature, kind of like your car in the summertime when you have to park in the sun. It's going to absorb all that sunlight, but then what will happen is it will heat up. It will emit based on its temperature, and you'll feel that infrared energy or that warmth. Now, we're going to talk about the macroscopic form of optics, where we're looking at what are called ray diagrams, and we're only going to worry about the direction of the propagation of the wave. And for now, we're going to assume there's no absorption or emission based on the object that we're looking at. The light just passes through, although in the really real world, that's not exactly true. So when we talk about light, light is an electromagnetic wave, and there's a lot of different forms of it. X-rays are light, infrared, which is heat, is light, radio waves are light. Now, understand when I say radio waves, I don't mean the sound coming out. I mean the electromagnetic signal that has to get to you from the radio station or the cell phone tower or whatever. So you've got a chart in your book, and we've also got a chart that I'll show you, but we can see we're what are called trichromats by and large. There is some evidence that people may have, some people may have a fourth cone, but we are trichromats, meaning we have three color cones, red, green, and blue. But the combination of those, we can distinguish about, on the average, about 10 million colors. And other examples of this are bumblebees and honeybees are also trichromats, but they have ultraviolet receptors instead of red. And then the rainbow mantis shrimp has 12 color receptors. So it's the winner when we talk about color vision. So when you look at the chart of the electromagnetic spectrum, what you see is, even though you don't think about this, you interact with a lot of the electromagnetic spectrum on a daily basis, whether it's through x-rays or baggage screening, or you go to the dentist and they cure your filling, or you have a mobile phone or whatever. So you see all the different parts of it, but also what I want you to notice is just how small a section we actually see with our eye. That little colored section there with the rainbow in it is the only part that can actually be detectable by the human eye. And that's a pretty small section of all the light that's out there. And then I thought this was interesting because what this is a picture of the radio frequency spectrum, where we see radio waves are auctioned off. Basically, the FCC in the United States auctions off the radio spectrum, and it's bought by either TV stations or radio stations or mobile phone carriers or civil defense wavelengths or whatever. So it's pretty big spectrum. It's pretty interesting how it's auctioned off. Okay, so light travels at different speeds in different materials. Now we think about the speed of light as being constant, and that is true when it's in the material, but it's not the same as it is in vacuum. Light goes the fastest in vacuum or empty space, and then it slows down because the electric and magnetic fields interact with the medium. okay? But light is a self-propagating wave. It doesn't have to continually have a source of input to move it through the medium. Like when we talked in the first unit about having to like flip a rope or constantly supply a sound wave vibration or something. You don't have to do that with light. Now, how fast light goes in a medium is determined by something called the index of refraction. And the index of refraction is just the ratio of the speed of light in vacuum, which is a constant, 3 times 10 to the 8th meters per second, to the speed of light in the material. Okay, so it's a fairly straightforward calculation. The ray model of light is we're going to look at just straight lines. We're not going to worry about the organization of the electric and magnetic fields. And light rays can cross, but they don't interact necessarily, which means that if it's an outgoing ray and an incoming ray, they ignore each other. They don't interact. And then when it gets to a boundary, you have to figure out, is it refracted, which means bent, but it still travels in the same direction? Is it reflected, which means it'll go back into the medium that it's came from? Or is it a little bit of both? And we'll see how to figure that out. Now, in the material, really, we know light can be scattered and it can be absorbed, but for our models of ray tracing, we're not going to worry about that. And then how we form an image is we look at the light rays focusing, and there's several sets of notes coming up about how we can look at that. So we're going to look at reflection first because it's really the simplest, and we're going to look at the simplest case of reflection, which is organized reflection off of a smooth surface called specular reflection. So that's what you think of when you think of reflection, seeing yourself in a mirror or a shiny surface or something like that. So then diffuse reflection is reflection off of a rough surface, and that's how we see each other. We see the reflection of the light off of our clothes and off of our skin and whatever. We see by the light that's reflected from coming out of the light source gets reflected off of us, and that's how we see each other. And we know that because when I turn all the lights out, we don't see each other because we're not giving off visible light rays, we're giving off infrared. And we're always going to assume that everything stays in the same plane, that it stays in a two-dimensional plane or in the plane of the paper or the blackboard or whatever. So reflection does not change the material it's traveling in. It stays in the same material, therefore its speed does not change. So what that means is there's no change in the path of the light other than it's just reflected off of the object. So it's very easy for specular reflection because the angle of incidence equals the angle of reflection. So you're going to have a line that you draw that's perpendicular to the surface that's reflecting off of, and you're going to measure the angles from there. And you'll see that in a drawing here. Then refraction is where the light changes the material that it's in. So the speed changes. So the path has to alter. I think of it as people marching down a road and then part of the road is washed away. So the people marching in the mud have to change their stride in order to not slip or fall down. So even though they're trying to stay in line with the people or in step, they get behind, they lag behind. So what ends up happening is the line formation changes or bends at that boundary between the mud and the pavement. And that's a lot like what happens with the light. So the index of refraction, N, is just the ratio of the speed of light in vacuum, which is 3 times 10 to the 8th, to the speed of light in the material, whatever we determine that is. And the larger that number is, the slower light goes in the material. The index of refraction of air is pretty much 1. It's like 1.0003. So we'll use it to be 1. Okay. Refraction also allows us to form images. So light occurs, or refraction occurs when you have light moving from one material to the other. Now, if it goes slower in the second material, say it's going from air to water, then what will happen is the light ray will bend toward that normal to the boundary. And if it speeds up, which could be going from water to air, for example, then it will bend away from the normal to that boundary. And I've got a drawing of that coming up. So this change in speed is what causes the path of the light ray to alter. It allows the light ray to bend, and then it will start at a new constant speed as it continues to travel on through the medium. Okay, so the other thing that happens is because it changes the material that it's in, it is wavelength dependent. So different colors of light may have different indices of refraction in that material. So blue light may bend slightly more than red light. And this is what happens when we see a prism, for example. That particular type of material has a different index of refraction for the different colors of light, and it disperses them or spreads them out because they all bend through slightly different angles. So there's an example of refraction. You've got your angle of incidence measured from the normal. You've got your angle of refraction. Since this medium must have a higher index, medium 2, than medium 1 does, the light ray slows down and it closes that angle up. So the angle of refraction is less than the angle of incidence. If that were reversed, then you could think of it as opening up. So if you were to imagine it was going the other direction, for example. Now, the way we calculate how much this happens is we use something called Snell's law, and Snell's law determines the angle of refraction for different materials. It's because the energy has to stay constant. When you travel into a new material, you can't create or destroy energy. Energy has to be conserved. So what ends up happening is the energy or the frequency will stay constant because that's what we use to determine the energy. So this ratio has to stay constant as we use Snell's law. So it's the ratio of the index in the first material times the sine of the first angle measured from the normal is equal to the index in the second material times the sine in the second material. And we're going to work examples of this so you'll see, but the product has to stay constant. Sometimes you can get an example though where you get a little bit of both, because if you can imagine you're going from a lower or a higher index material to a lower index and the light speeds up, that angle opens up, it gets larger. So what ends up happening is there comes a point when that angle will get so large that it's 90 degrees. And so what happens there is at that point, we reach what's called the critical angle. All right, at that point, some of the light is going to get trapped in the first material through a process called total internal reflection. We still use the same concepts, but we apply total reflection for the part that gets reflected back in the first material and refraction for the part that makes it through. So it only occurs when you're going from a larger end to a smaller end and the light is speeding up. So say you're going from water to air, then you could possibly have total internal reflection. And that's what's happening in this picture. You're in the water, you're looking up toward the boundary with the air. Some of that light is reflecting back into the water. So you're seeing the reflection of the turtle in the water boundary. It's also responsible for how things like fiber optic cabling works, because we reach something called the critical angle, and the critical angle has to do with the two materials. So it's different for every combination of materials. So the sine of the critical angle is the ratio of the lower index number, the second one, to the higher index. So it's always going to be 1 or less. And whatever that is the angle that if you come in larger than the critical angle, you'll get reflected back. So this is how light works in a rainbow, because what happens is the sunlight comes in, it gets dispersed by the water. So it's going from air to water, so it slows down and gets dispersed. But then when it hits the back of the water droplet, it's trying to go from water to air. And some of it will not make it out because it'll be coming in at too large of an angle to be able to transfer on through. So it gets reflected back toward the viewer. That's why you only see rainbows on the horizons, because that's where you have the proper angles to have total internal reflection. Now, another example of refraction is when you have any kind of material where you're going from one to another. You have basic refraction and you just use a ray diagram, but you apply Snell's law at each boundary. So you have to say, for example, in this picture, you'd have refraction going on at the left-hand boundary. You'd work out Snell's law, you'd find your new angle, and then you'd have refraction going on at the right-hand boundary. You'd work another Snell's law problem there. And you have to use a little bit of geometry to figure out what the angles are. Okay, so you have to use geometry to find the correct direction change. You always measure the angles from the normal to the surface they're interacting with. So you would draw a normal to the first surface and measure all your angles from that, and then you forget about that, and you move on to the new surface and draw the new normal and find the new angle. Okay. This is a little drawing. Oops, this is a little drawing of total internal reflection here. So you've got an angle coming in less than the critical angle, goes right on through and obeys refraction. But at the critical angle, the red line, it comes in and it's reflected right along the boundary at 90 degrees. And then for glass, or excuse me, for the blue line, it comes in larger than the critical angle, so none of it will make it out. It will all be totally internally reflected. So the critical angle is the break point between whether it gets refracted or whether it gets reflected. The Doppler effect for light is a little bit different than it is for sound because the waves are self-propagating. So when you look in your formulas, they're going to look different, but it's still a case of the frequency goes up for relative motion toward and down for motion away. Polarized light is where you look at light, where you select out part of the electric fields. It's kind of like trying to walk through a doorway with a very large, say, sofa. You have to turn the sofa to fit the opening. So what the polarizer does is it selects only the part of the light wave, and it looks at the electric field part of the light wave that can make it through the opening. So what it does is it reduces glare, but it also dims the light. So polarized light is slightly less, or is less in intensity than the original light, but it's organized in such a way that you don't get glare. So that's the advantage of polarization. Polarizing filters, like I said, will select out the part of the light wave, and the light will take on the polarization of the filter. So in this picture, what you see is unpolarized light coming through. Automatically, half of our intensity is lost when we have unpolarized light. Then that light goes on through with the new organization of the first filter. Then when it hits the second filter, it has to look at the angle between the light and the second filter. So in this case, it's 90 degrees and none of it makes it through. But you look at the relative angle between where the light came from and the next filter it's trying to go through. Now, if the light is already polarized when it gets to a filter, instead of just saying we reduce it by half, we use something called Malice's law to be able to calculate the intensity. And Malice's law is where you look at the angle between the first filter that it went through and then the one it's coming through now. So the one it came from and the one it's going to, and that's the angle that you use. That's phi, okay? And so you take the cosine squared of that multiplied by the intensity that came out of that first filter, excuse me, multiplied by the intensity that came out of that filter. So you're never going to increase the intensity of the light using a polarizing filter. You're always going to knock it down. And how much you knock it down has to do with the relationship between those angles. There's other ways you can polarize light. You can polarize it through reflection using something called Brewster's angle, where you have like a surface like water or glass or something. You can partially polarize light doing that. Another way you can polarize light is through double refraction, which is like a calcite crystal has a property called birefringence, where it splits light up. It splits light up into two rays and they're both polarized, which is a useful way to polarize light. Okay, so that's where we're going to end this set of notes, and I'll come back with a few more.